fourth paper of the series on statistical strong lensing, and the subject is redshifts. Redshifts are the elephant in the room in conversations about the future of strong lensing. If we want to use a lens to measure mass, we need to know the redshift of both the lens and the source. Usually we take spectra for that, but if we're going to discover tens of thousands of new lenses, it's going to be difficult to follow them all up. Can we use photoz's? Maybe, but even that is difficult because the lens and the source are usually blended and the lens outshines the source. The solution that I propose in this paper is to use a method called photogeometric redshifts. The idea is this. The angular size of an Einstein radius depends on the redshift of the lens and the source, which is the geometry of the system, and on the mass of the lens. If we knew everything about the lens, we could use that information together with the Einstein radius to measure the redshift of the source. Of course, we don't know everything about the lens. In fact, usually the whole point of the strong lensing observations is to actually learn about the lens properties. It sounds like a vicious circle, but the solution is to infer both the lens properties and the source redshift simultaneously in a statistical sense. It's not easy because it involves modeling the lens selection function, but what makes it possible is the formalism that I developed in paper 3. I applied this method to a simulated complete set of lenses with no individual source redshifts. And the nice thing is that in terms of precision, there's not actually much difference with respect to the case in which the redshifts are known. So we should still get as much telescope time as possible to follow up strong lenses. This is because strong lensing is always a good investment in terms of science per spectrum ratio. But if we don't, this is the alternative. Thanks for watching.